Okay, Cristiana. Okay, good afternoon. Here we are for another seminar, a remote one, of course. And our speaker today is Cristiana Spingola from IRA. Just to introduce her, she graduated in Bologna with Daniele Dalla Casa as a supervisor, and then she moved to Groningen, to the Kaptein Institute for her PhD under the supervision of John McKean and Leo Koopmans. And she got the PhD finally in 2019. She also spent some time in Astro in Dwingelhof for a postdoc, and since September 2019, she moved back to IRA, and she's now working in the VLBI group. And today she will tell us about gravitational lensing and VLBI to study the matter distribution in galaxies. Please, Cristiana.
Okay, thanks a lot, Franco. Today I would like to talk to you about the jetted AGN view as seen using strong lensing and VLBI. So the results I will show today, they are from a collaboration with many people, which I listed here. And so why do we care about jetted AGN? We believe that radio jets may have an impact on the star formation rates of their host galaxy, and this impact seems to be more important in the center of the galaxies. Also, in this case, if there is really an effect of radio jets, they may affect also the coevolution between supermassive black holes and the host galaxies. And in particular, this coevolution and this effect should be related to the kiloparsec and sub-kiloparsec scales. So we may test some predictions of the effect of AGN jets or jetted AGN in galaxies from, for example, the lambda CDM hierarchical scenario. So, for example, the lambda CDM model predicts that galaxies grow via merging, and therefore also their supermassive black hole may grow via the merging of multiple supermassive black holes of the merging galaxies. So, as a consequence, we may observe the presence of multiple supermassive black hole systems in the center of galaxies, which can be dual AGN, if, for example, we have two supermassive black holes both active, or offset-AGN, if only one is active. And this AGN may be jetted, and so the jets may have an effect. Also, as a result of the merger process, we may have as a remnant a red compact stellar cores, again in the very center. So for all these reasons, center of galaxies may be a good laboratories to study the jet host galaxy connection, but the scales which I am talking about are really small. So I'm talking about less than a kiloparsec or hundreds of parsecs in size. Therefore, they are easy, not that easy, but easier to access at low redshift. But it becomes very difficult to access these scales at high redshift. So that's why gravitational lensing may help us, because galaxies may act as cosmic telescopes. So just to be on the same page here, I recap what strong gravitational lensing is. So we may have a background source, in this case, extended AGN jets. And between us and this source, there can be a massive object. And in this case, we have a single elliptical galaxy, but it can be also a cluster of galaxies. So the light emitted from the background source may be deflected and magnified into multiple images of the same background object. So in this case, you can see these images, which are a distorted view, an amplified view of the background source. They are connected, forming the extended gravitational arcs. And this is because of the lucky alignment between the background source and the lensing galaxy, but also because the background source is intrinsically extended. So this is not so common to see such arcs. But anyways, these kind of lensed objects, these lensed images, are very powerful to study the mass distribution of lensing galaxies, and they have become a powerful tool for studying, for example, substructure in galaxies. But they are also providing us a very amplified and magnified view of the very distant background source. So in this case, sources that would have been too faint to be detected, they become visible. Therefore, this is a very powerful way to access the very distant and faint universe. And in this talk, actually, I will focus only on the source plane and on the source science. So we can take advantage of gravitational lensing and the combination with high angular resolution observations to really have the highest angular resolution. And at the radio wavelengths, this very high angular resolution is provided by very long baseline interferometry. And here I'm showing you some examples of interferometers, of arrays of antennas that linked together, they act as a single telescope with diameter equal to the maximum baseline between two antennas. So I'm showing you in the world map the European VLBI network, which includes actually 3 Italian antennas, Medicina, Noto, and Sardinia, which are highlighted in yellow. And then also the very long baseline array in the US and the very large array in the US in Socorro. These are the arrays that I used for the results I will show you later. So there are several pros of using interferometry and in general radio wavelengths for studying the strong lensing systems. So one, the most obvious maybe is that we have very high angular resolution, which can be even at sub-milliarcsecond level when we observe at gigahertz frequencies. This may lead to microarcsecond astrometric precision on the position of the lensed images, which are the constraints to the mass model, and therefore, thanks to the lens mass model, the precision on which we know the mass distribution of the lens, we can reconstruct the source plane. Then we have no problems with the dust obscuration of the lensed images because of the lensing galaxy, and there are no microlensing effects. So I just want to say one thing, because going to the cons, usually one of the main cons of VLBI is the very small field of view. But in this case, I will talk about galaxy-galaxy lensing, and the image separation is usually at arcsecond level, and so this is not an issue in this case. But the main con that we have is actually the very little statistics, because we know only 35 radio loud lensing systems to date. And this is a combination of the strong lensing probability, which is 10 to the -3, and the fact that the radio loud AGN, the jet, the AGN population, is only less than 10% of the total AGN population. So I will divide the talk in 2 parts. Phase 1, where we will use what we have at home, and basically with the data that we have so far, we can constrain very well the center of galaxies. So I will combine strong lensing and VLBI, but also high angular resolution optical observations to test dual AGN, offset-AGN presence, and compact stellar cores at high redshift. Then in the second part of the talk, I would like to try to address the small statistics that we have and search for new radio loud systems in wide field VLBI surveys. So we start with the first part, starting with the possible lens dual AGN systems. So what is a dual AGN? Just in a very short summary, dual AGN systems may look like these systems I'm showing you here. So we may have multiple flat spectrum components, so 2 flat spectrum components, or 2 X-ray sources, but also misaligned jets. And in the case of spectroscopy, we should observe multiple peaks in the narrow emission lines, meaning that we have in the same host galaxy maybe 2 narrow line regions. So we expect a low fraction of the system in the local universe with about 0.1% at redshift 0, but the fraction goes up to only 2% at redshift 2. So considering the strong lensing probability, finding a strongly lensed dual AGN should be very rare. So we think that maybe we have found one, which may be 2016 plus 1112. The system I'm showing you here, the HST imaging, has a very complex configuration where images A and B actually are doubly imaged, so they are probing the same part of the source plane, while image C actually is part of the quadruply image, quadruply image system. And so it's probing a slightly different part of the source plane. Images A and B shows an unobscured morphology, while image C shows an obscured morphology in the optical. The source is at redshift 3.2, is lensed by a galaxy cluster, this is the main lensing galaxy in the center at redshift 1. It is X-ray loud, all the three images are detected with the Chandra observations, and it shows very complex properties when observed with the CFHT. So this is an early spectrum of spectra of images B and C, where Yamada et al. In 2001 could not fit with a single photoionization model these two spectra, meaning that maybe we have two different ionization levels in the region related to image B and the region of the source related to image C. When we observe this with VLBI, we can actually spatially resolve the lensed images in several subcomponents, and in particular we have two components that are flat spectrum, while the rest of the components that are steep, that show a steep spectrum at the radio wavelengths. So this is the global picture that we had of 2016, but recently we have obtained another VLBI observations of the system at 1.7 gigahertz, and I'm showing here on the right the overlay of the contours, where the white contours indicate the epoch 1, and the red contours indicate the data obtained in 2016, so the epoch 2. And so these observations actually revealed the presence of positional change, and this positional change is particularly evident in image C. You can see also this very basic GIF in the bottom left of the slide, and this image is the image at the highest magnification in this system. Actually, this is the highest magnification for the radio loud strongly lensed system, with a magnification factor of about 300. So this positional change, let's say any change in the system configuration, may be more visible in image C because of this high magnification. And this change may be due either to a motion of the lensing galaxy or to a motion due to the source plane. Our lens model could rule out that this motion is actually due to the lensing galaxy, but we attributed entirely the motion to the source plane. So what we found when we reconstruct the source is something like this. So this is a very crowded slide, but on the left we have the mass model, and on the right we have the source plane reconstruction using a parametric approach. So there is a vertical blue line which divides the source plane into regions. This line is the caustic line and indicates the region where the magnification goes to infinity. As you can notice, there are 2 points here very close to the caustics on the right side, the quadruple image part, and these 2 points are those related to image C, and that's why they are at high magnification. So we found that these two components, a core and jet component, have moved by the same amount in the same direction with a proper motion of about 3 microarcseconds per year, while in the other part of the source plane, those related to images A and B, one component, the core, is consistent with no motion, while the other actually is moving at superluminal velocity in a different direction with respect to components 3 and 4. So this made us think that maybe these two components, 3 and 4, so this core jet, actually is forming a bound system on the right side of the source plane. And therefore, we are maybe looking at a dual AGN system, also considering the previous multi-wavelength properties of this system. So preliminarly, I can say that we have modeled the Chandra observations, which also show that there is X-ray emission in both the doubly and the quadruple image emission, and it seems that the most favored scenario is when we have two X-ray emitting sources. But in order to constrain better the system, this is not enough, or at least to claim that this is indeed a dual AGN, and therefore we have obtained ALMA, MUSE, and global VLBI 5 GHz observations to actually constrain better these properties. But in the meantime, if we consider this to be a candidate, but a genuine, dual AGN system, then we can estimate what is the probability of obtaining a dual, of observing a lens, the dual AGN, which seems to be an order of magnitude higher than what predicted by current simulations. So this is important to understand because we may need to rethink about the fraction of dual AGN at a high redshift. But this was a case where we may have observed, so this is still a candidate, but we may have observed 2 active supermassive black holes. What if only one of the supermassive black holes is active? In this case, we may observe the system as an offset-AGN system. So in this slide on the left, I'm showing you some examples of offset-AGN from Barrows 2016, where they compare the optical emission, the red cross, with the Chandra emission, which is the cyan cross. And you can see that in these cases, there is a kiloparsec offset between the X-ray emission and the optical emission. So these kind of studies have been performed mainly in the local universe. In particular, these samples goes up to redshift 0.2. But offset-AGN do not necessarily mean dual AGN systems. They can also be recoiled supermassive black holes. So they may have been, the supermassive black hole may have been displaced from the center by, for example, interaction with a massive perturber. And the decaying oscillations for this recoiled supermassive black hole to go back to the center may last up to 1 gigayear. Therefore, this kind of displacement between supermassive black hole and the stellar core in galaxies should be quite common. But of course, to test this at high redshift, for example, in the range where galaxy mergers were more often happening, we really need to improve on our spatial resolution. And I hope I have convinced you before that lensing can really provide this spatial resolution. Here I'm showing this again with a different example. We have here on the right an example of a lensing configuration where in the zoom here on the top right, there are several source subcomponents, each different symbol, separated by steps of 1 milliarcsecond. When lensed into when lensed into the lens plane, we have these lensed images A, B, C, and D, and you can see that the small offsets in the source plane can become large offsets in the lensed images. So with the separation between the subcomponents up to 50 milliarcseconds. Of course, this kind of offset is much easier to be detected given the current instruments, and this is also telling us, of course, that the systems at a higher magnification are at a prime for studying multi-wavelengths offset in a distance object. So we started to select systems in the class survey. This is a radio loud lens survey of flat spectrum components. This is the only one that is complete. And as it targeted the flat spectrum radio sources, it means that we are looking at the base of the jet, which is also the closest to the supermassive black hole, and we can use it as a proxy for the position of supermassive black hole. And as they are not so many, they are plenty of multi-wavelength information, so they're really a good sample where to start to study this. So we looked for the quadruply imaged systems, and in particular those that have a robust lens mass model, and those that, let's say, we do not know very well the source plane. Some of them have been studied since the early 2000s, of course. So we selected 2 of these systems, which are 0712 and 1608, that matched our criteria, but I will also show results for the lens plane of 1938. But for this analysis, I will focus first on 0712 and 1608. So here I'm showing you how the system B0712 looks like. This is a lens, the AGN at redshift 1.3, and it is lensed by an edge-on spiral galaxy. You can see a little bit of this emission on the left. In the HST imaging, we have 4 images, A, B, C, and D, which are quite compact in the optical, but also in the VLBI, as shown in the right. This is a VLBI image at 1.7 gigahertz obtained with uniform weights. Image D is not detected in using uniform weights, but it is detected when using natural weights, so the position here is obtained with natural weighting scheme. So when we apply a simple parametric model for reconstructing the source plane, this is what we obtain. So on the left, you can see the lens mass model, and on the right, the source plane reconstruction. And here we do not find a significant optical VLBI offset within the central hundreds of parsecs. You can see here I'm calling optical point the brightest pixel of the HST image. And the radio emission has very, very small uncertainties. But here I just would like to highlight that I'm not considering only the uncertainties on the observations, so on the lens images, positions, and fluxes, but also the uncertainties on the lens mass model parameters.
In 20 minutes.
Okay. So in the other system instead, we have a much more beautiful optical emission. You can see here the images are extended, the source is at similar redshift actually, and in the radio it's shown on the right. You can see these 4 blobs, which are again the lens images, pretty much compact. And when we reconstruct the system instead, we find a marginal VLBI optical offset of on the scales of about 200 of parsecs. So this makes 1608 a good candidate for being an offset-AGN at high redshift. And if we put this in context of other searches for offset-AGN offset-AGN, sorry, at high redshift, here you can see the global picture. I'm showing in the y-axis the relative angular separation between either the radio or the X-rays versus the optical, and on the x-axis there is the redshift. And you can see that the highest redshift part of this plot is actually sampled only by VLBI, so with class B1608, but also Frey 2013. So this is a very simple method, and that can be used to find lensed offset-AGN at high redshift, and that can also it can also be applied in an automatic way for future large surveys, for example with the SKA and LSST, if they will have matched sky areas. So I will just take 2 slides to say that offset VLBI between optical and VLBI, sorry, it does not automatically mean offset AGN. So if we observe this kind of not co-spatiality, it doesn't mean that we are looking at an offset AGN. Here I would like you to focus on the white contours and red images, where the radio is indicated by the white contours, while the Keck adaptive optics at K prime filter is shown in red. These 2 systems are lensed galaxies, one at redshift 3, 0751 on the left, and the other at redshift 2 on the right, P1938. If we reconstruct the multi-wavelength emission, this time with a pixelated source reconstruction, now we can have a multi-wavelength view of both these systems at very high redshift. And you can see in the case of 0751 on the left that we have these extended jets on 1 kiloparsec, again white contours, but at the center, like between these 2 jets, we have this very compact stellar core, which may be the remnant of a merger as predicted by simulations. On the right, we have a similar situation where we have a compact stellar core in the center, but in this case, the 2 radio components actually are hotspots of a compact symmetric object. Just a note, this is a powerful way also to unveil the distribution of cold molecular gas at high redshift. These observations I'm showing you here are the CO120, is the CO120 emission in these systems, which is usually at very low surface brightness and therefore very difficult to access at high redshift. But I hope that I have convinced you that even if we study a few strong length AGN, this can already provide us a lot of information on the central part of galaxies, and especially if we combine the VLBI observations with a multi-wavelength approach. However, we have still the issue that we have a few radio loud strongly lensed AGN. So we searched for new radio loud lensed AGN in the MGI-20 survey. I will just skip all the details. This is just a single slide on this. But this wide field VLBI survey is very powerful, and it targeted the medium faint radio source population. On the left, I am showing you a pointing where the angular resolution is of about 11 milliarcsecond square. And we applied, for searching for these lens systems, very simple selection criteria. So simple in the sense that there must have been at least 2 lensed images, the surface brightness must be conserved, the flux ratios between the different components must be sensible to be a lens system. And so with this simple selection criteria, we came out with a final sample of 14 lens candidates, where among them 2 were actually rediscoveries from the class survey, making this like a proof of concept that the method, even if simple, actually worked. And we followed up the systems with VLBA at C-band, which means at 4 and 7 gigahertz simultaneously. And this made the follow-up at multiband very efficient, because in one go we had 2 frequencies, and we ended up with two final lens candidates, and a lensing rate that is consistent with class. It's not surprising because our error bars are very large, but this is just to show that if we start directly with a VLBI survey, we may already have a lot of information, and we can still find strong lensing systems, and this may be considered observationally efficient, because if you consider that class had several intermediate steps with the VLA at lower angular resolution, here we are actually skipping all of those steps, which means a lot of hours, hundreds of hours of observations with the VLA. So this is a promising way. And we still need to follow these 2 lenses up with the spectroscopy to understand this better. But I will just conclude here with the take-home messages. So gravitational lensing and VLBI can really allow us to access the parsec scales of distant galaxies, and in particular the central parts of galaxies, which are important to test galaxy formation and evolution predictions. If 2016 was found to be actually a dual AGN system, then this made us rethink about the fraction of these systems at high redshift. But proper motions have been proven to be a powerful tool to check the nature of these systems at high redshift. So if we combine the VLBI with the optical at high angular resolution, we can also unveil parsec scale offset-AGN, but also more complex systems like AGN jets hosted by compact stellar cores. And finally, wide field VLBI surveys seem to be observationally efficient for such radio loud lens search, and all the methods, or most of the method that I showed you today, can be automatized in vision of the future large samples of lenses. And I'll stop here. Thanks for your attention.
Okay, thanks. I changed the soundtrack for the applause. Okay, so other questions for Cristiana? Experts, non-experts? Anybody?
I have a question, Cristiana, about the offset. I guess that the observations you use for comparing positions, optical and radio, are not simultaneous.
Yes.
Are the offset within the possible relative proper motions of the system between the background source and the lensing object?
Okay, on top of my mind, I do not know the exact numbers, but I should estimate it. But yeah, the observations are separated by of about 10 years, so it still may be that there can be a possible change in the lensing galaxy position. But I should estimate it, so I don't know. I don't know.
Okay, thanks.
I can read the questions that appeared in the chat by Vincenzo Antonuccio. How sensible are source reconstructions to systematics like the details on the lens mass distribution?
Okay, so in the case of the parametric models, we have pretty robust lens mass models, which are very precise. They are all modeled with singular isothermal ellipsoids or power law, and the precision is on the lens mass model parameters is of less than 10%. So I believe that the reconstruction is pretty robust. In the case of the pixelated source reconstruction, there are other systematics, so of course, yes, that must be taken into account. But just to be clear, the relative position of the different components is robust. So I believe that there is no strong effect on the reconstruction from this.
Okay, I think that's enough for that question. I mean that covers the question. And we have another by Piero Rosati. Is there any evidence of variability in your lensed AGN targets?
Okay, this is a very good point. So in the all of them, they have many years of monitoring, except 2016 and 0751, which didn't show variability in the 4 epochs that we have, but the others actually they do not show significant variability in the radio. So it's less than 5% variability, if I recall it correctly. I can check it up, but that's a good point because the reconstruction depends also on that. Okay.
Waiting for anybody else to ask a question. I have just a curiosity. Maybe it's a stupid one. Taking your strongly lensed dual AGN, the first one you discuss MGB whatever. Okay. Is there any way to estimate even orders of magnitude what is the chance to observe a system like this, or you cannot do like a posteriori statistics just based on one object?
So that's what we tried to do. I have to say that 2016 doesn't come from class as a lens search. So in class we know the selection criteria. So the sample is complete. While this is from the MIT Green Bank survey, so the MG survey, for which we do not know all. It was a completely different survey. So what we try to estimate this, and that the number I put in the slide actually the 2 × 10⁻⁴ probability of finding a lens dual AGN comes from this estimate. Okay. But it's very, very hard to do this in this case.
Okay, I see. Okay, let me see if there are no more questions.
I have a question.
Yeah, please go.
So I understand that these VLBI observations are quite challenging. You need deep sensitivity, wide field of view, so that they're not very easy. And these are probably the most prominent targets, those that were relatively easier to find. I wonder about these future samples of lenses that SKA and LHC.
C-band seems a very promising way to follow these sources up. So I would say that the current development of C-band is one of the way to go, at least in my opinion. But if we want to follow up all the systems, that's not possible. So we need to come up with selection criteria to follow up only the interesting one for each science case. Or that can cover more than one science case.
Okay. Okay, any other question? Okay, if not, let's thank again virtually Cristiana. And of today, we will be next week. I think the next speaker is Lorenzo Lovisari, yes. And by the way, we are looking for 2 speakers for mid-June, the 16th and the 23rd. If anybody online is willing to give a remote talk, please get in touch with me or anybody else in the organization. And otherwise, see you next week. Thanks, Cristiana, again.
Thank you. Thanks a lot.
Ciao, Cristiana.